Welcome to part 2 of our Kornucopia ML Quick Start training. This is the second of 8 videos for this course. Please visit our website at boditech.com for additional details on downloading the accompanying PDF course notes and other training files. I'm now going to step up the game a little bit, and we're going to do a little bit of an engineering calculation. And this will start to explain the power of K units, the power of tracking with units, doing calculation with units, and such. So we have a cantilever beam here, and we have some parameters for the beam. And the parameters are the length of the beam, height, and width, which is the depth, and the modulus, as well as the volumetric mass density. And if you were to go look up in a book when you have a distributed load for its own weight, this is the kind of formulation you would find for the deflection of the beam at any location. And we want to compute the deflection at the end of the beam. So that would be when X is L, pumping it into this formula. And we would like the answers out in terms of millimeters and then also in inches. So what I'm going to do is I'm going to open up in the editor and I will demonstrate creating this. And then I will demonstrate putting in these equations, although I will most likely skip most of these comments, but they're there for you in the files you have. So you have a folder that was given to you that you downloaded for this course, and it has a folder called snippets. And in the snippets will be the various little scripts that are for these kinds of calculations. And if we put this in and do these calcs, which I'm going to do live here in a second, you'll find that Kornucopia will readily compute the maximum displacement in terms of millimeters or in terms of inches. So I'm going to do this live right now to show you. And I'm going to start with a blank slate and do that live. All right, so the first thing I'm going to do is I'm going to clean up my workspace. And this function is not required for you to be used if you're a Kornucopia user. I personally find it helpful because it's interactive, and I don't just automatically open up some script and without knowing it, blow away 3 hours of work that I just had and some other deep, complicated calculations that I had by having clear all just automatically run. I'm given a pop-up so I can make a choice of whether or not I really want to clean up the workspace. Now, in Kornucopia, when we do calculations, Kornucopia needs to determine what units to give the results in. And so this is defined by something called a units preference. And I'm going to talk about that a little bit more in a moment. For now, just accept that I'm going to enter this command, units preference activate, which is going to tell Kornucopia what units preference I want it to turn on and use for these calculations. And to start with, I'm going to put in a question mark. And when I highlight that and hit F9, F9 is MATLAB's calculate command, this little one line gets calculated. And because I put a question mark in here, Kornucopia will give me this pop-up to select from one of a variety of known unit preferences. So again, we will learn about what these are in a little bit. For now, just accept the fact that I'm going to put in this millimeter Newton per second preference. And now that I've defined that and it's active, I'm going to actually put that in here so that if I were to run this script later, like tomorrow, I wouldn't have to make the selection. I would already know what preference I want to run. So in our beam problem, we've got some parameters for the beam, and they were in different sets of units: feet, millimeters, inches, KSI, kilograms, and meter per cubed. So normally in a normal MATLAB or Excel or Python workflow, you would first have to convert all those to some common unit system to then be able to do the calculation. In Kornucopia, you do not have to do that because Kornucopia will do all that for you because you're going to work with actual units. So let's go define a couple of variables. We'll define the length. I'm just typing K_units, and the length of this beam was 1 foot. So I'm literally typing that in. Now, the various units that I'm going to be putting in here, we're going to learn shortly that Kornucopia has a unit system with well over 200 known units in it. And it's flexible so that you can even add more units to it if you have some units that are not in it already. but it has many of the normal units you would be accustomed to using. And so that's why Kornucopia knows that that's a foot. All right, so we're going to find the height here. And I'm going to find the depth. And the modulus. Now the modulus was shown as 29 times 10 to the third KSI. So the way we're going to write that in MATLAB format would be 29 E3, that's 10 to the third. And then the units is KSI. And you can't type in Greek letters for variables, so we'll type rho for the Greek letter rho. And we'll put in the density. Now, just so you can see the variables echo, I'm going to remove these for the moment. And I am going to run this section. And you see the various results are exactly as I've requested them to be. So we now have our data, so now we need to start to calculate stuff. So in the formulation of the beam, the first part of the problem, we're going to be defining a weight, and it's divided by EI. So the first thing we're going to calculate is I, and then we'll calculate a cross-sectional area, and we'll use that and the density to get the mass of the beam, and then the mass of the beam divided by its length and also multiplied by gravity to turn it into a weight will allow us to get this parameter W, so we can then ultimately put in the final equation. So I'm going to put in a few of these things. So just for brevity, I'm skipping the comments that were put in the actual snippet that you have. So for a beam that's rectangular, the moment of inertia for bending would be 1/12 BH cubed. So that's the moment of inertia. And actually, I'm going to just calculate that right now. So I'm going to highlight that and hit F9. And you'll see that Kornucopia readily handled the fact that B was in inches and H was in millimeters. And Kornucopia did the calculation, and it did not take the number of 3 and the number of 1 and just, apply them in the formula. It converted them internally to a common set of base units, did the calculation, and then returned the result in the unit preference that you had said you wanted results in. So I have stated here I want the units to be being returned in any results that are done with math to be in terms of units like millimeters, newtons, milliseconds, and other units like that. And actually in the example, I did not use milliseconds, I did seconds. So let me just change that. So I'm going to do this on the fly. So I'll put that to the millimeter Newton second system. And in a minute, we will learn what all these systems are and all the other units that are associated with them. So I'm just going to recalculate that. So that wouldn't actually affect these because these are definitions, but it would affect this if the result wasn't in terms of millimeters to the fourth, because milliseconds isn't going to impact that. Okay, so now I've computed the bending moment of inertia. I'm going to go compute the area. And I will compute the mass of the beam. So that's the volumetric mass density times the area times the length of the beam. Now, we need to turn mass into weight. So we're here on Earth, so we need to multiply by gravity. The unit, capital G, is the standard unit of gravity, and Kornucopia knows about that. So we're going to set a variable name equal to the unit of 1G. So I want to explain something here. So when I do this and I calculate that, this is a variable name. I could have said Bob is I could have done this and said Bob is equal to 1g. And then indeed, Bob is 1g. And then I could, in my formulations where I needed gravity, I could be multiplying by Bob because that's a variable. That doesn't, make the equation look very nice. So instead, I've made the variable g equal to 1g. So this is a k units entity, and its variable name happens to be g in this little calculation that I'm doing. I will speak a little bit more about that to clarify that topic, but that's one of the places that people sometimes get tripped up a little bit. And in a few minutes, we'll go over that topic with a few other examples to hopefully solidify that concept. And lastly, I'm computing the weight. And now I need to define that I want x to be at the length L. And now I'm going to compute the equation. So y max for the beam. So I'm just typing in the equation based on what was in the PowerPoint that I showed you a minute ago. So it's W divided by, and I'm dividing that by 24 times the modulus times the bending moment of inertia. And then I'm multiplying that by x raised to the fourth minus 4 times the length times x raised to the third plus 6 times the length squared times x squared. Okay, and we will evaluate that. And we have the calculation of the length y max. I'll push this up to the top so you can easily see that I'm typing the home command to make that occur. Y max. So now let's say when I did this thing, I made a mistake. So let's say the mistake I made was I put a square here instead of a cubed. If you were computing that in MATLAB, Excel, or Python, unless the answer that came out, you knew the number didn't look right, you would have no idea you made that mistake. But with Kornucopia, you'll get an error. And it'll tell you that an error around this operator. So the operation around that subtraction sign, there's an incompatible units error. And it's telling you that one of these things resolved to meters to the fourth and one of them resolved to meters cubed, which is of course incompatible units. That's one of the significant powers when you're doing just even engineering calculations with Kornucopia. It will save your bacon many times over for making mistakes like that. Now, correcting the mistake, calculation is correct as is. Now, we were told we would like the answer to also be put out in terms of inches. So we could reassign the value. And now I'm hitting dot and tab. And I'm picking a method. So from the variable itself, there are properties like dot props and the data, which is the number and the units. And there are methods. The methods are all start with lowercase. And the one I'm going to pick is convert. So I say I want that to be converted to inches. So if I do that and then execute that, now I have the value in inches. I don't have to remember any conversion factors. And in fact, you never, ever put in conversion factors in your calculations with MATLAB with Kornucopia. You put the data in as it naturally is, associated with appropriate units, and then let Kornucopia handle all of that. Now, if you look at the script, this was a bit of a lengthy thing, but that was the nature of the equation. The rest of this was pretty straightforward, I think. But up here, this was maybe, you could view this as a little bit annoying. I had to put all this K units thing all over the place. So we can instead do something a little bit different. So I'm just going to copy this so I don't have to retype it all. And I'm going to demonstrate one additional variation to this. I'm going to introduce, so I'm going to clean this up. So say yes. So now I have no variables. I'm going to introduce a new kind of function in Kornucopia called k_unit variables. And what I can do here is I can put in any units that I would like to be represented as variables. Just like I did g equals k units of 1 times a g, I can go in here and I can say I would like ft to be the units of feet as a variable. And I can put in mm, and I can put in in, and ksi, and kilogram, and meter. So now when I do this, and I compute these two things, now all these variables show up over here. And what are they? Like the variable kg is 1 kilogram. So now I can go here, and instead of doing this kind of thing, I can just say that's 1 times a foot. And this is 3 times a millimeter. This is 1 times an inch. That's 29 e to the 3 times ksi. And that's 786 times kilogram per meter cubed. Now, MATLAB here is warning us that I haven't ended with a semicolon. And it's saying you're going to be echoing stuff to the command window, which in this case I really would like to do. So I'm going to right click on this, and I'm going to suppress that warning in this file for the moment. I'm actually just going to put the suppression up here. So for the whole file, it'll stop warning me about that. Because whenever we make scripts in MATLAB, our goal is to make them green. We want to try to have scripts with no warnings and clearly no errors. All right, so now I'm going to run this section. And since I don't have a semicolon, everything will echo out over here. So I'll make this go to the top. So now when I run this, that was assigned 1 foot. But it was done so by math, not by assignment. When I did k_units, whatever we are assigning to the variable specific unit and data associated. Here, we're doing math. We're taking the number 1 and multiplying by the variable feet. And whenever we do math, the output is whatever the units preference is. So now L, even though it's 1 foot here, has been converted to 304.8 millimeters because we did math and we told the script, whenever we do math, store the output in these unit system. And that's true for all of these. So these are exactly the same as this. There's no difference. It's just been stored differently per se. And now I don't really need this command here because, especially if I go up here and put G in here, I didn't put G in here. So now there'll be a variable G over here as well. So now when I go here, I can do this calculation and it will still produce the exact same result as before. Most people would say that this is a nicer format, a little bit easier to use. And so I'm explaining and showing you different ways to work with this. So I'm going to just go back to the PowerPoint here because I have a couple pointers I want to make. So we first did it like this. We got our results. And now we've added this k_units variables approach. And then this, in my opinion, was easier to type, but we still come up with the same results. And I demonstrated that if you make a mistake in the equation, the cornucopia will save you by denoting there's an error and around what operator, what math operator the error occurred from a units incompatibility standpoint. It even gives you links to learn more about it. And since this was done in a particular script, it'll show you here what line in the script the error was. So Cornucopia tells you where the error was, and the Cornucopia error messages are quite rich with information. So some people, when they use software, they see a red error, they just like throw up their hands, oh, I got an error. You should really spend the time to read the error messages. They're meant to try to tell you, you had a mistake, this is what probably caused the mistake, and this is what you might do to try to fix it. So all the messages are like that. So read the error messages, they'll help you out. Now I also pointed out that when you define a variable with the k-units constructor, the output of the variable will look just like what you said it was. Whatever units you put in there, they will appear in the output representation. But whenever you do math, the output units of the resulting variable depends on the active units preference. Here we are doing a little example where the k-units variables are feet and kilonewtons, and the unit preference is in millimeters, newtons, and seconds. Now I'm just showing the output of executing that, where now in the workspace, the variables feet and kilonewton appear, their k-units data type. And if I were to type in the command window feet or kilonewtons, those variables would echo the response as shown. And now in this example, I'm defining variables with lowercase l and f using the k-units constructor to be 30 inches and 3 kilonewtons. And I'm also defining capital letters L and F to be 2.5 times feet and 3 times kilonewtons. So with the capital letters there, I am doing math. With the lowercase letters, I'm assigning variables via the k-units constructor. And then I'm just doing some simple additional calculations on line 16 and 17. Note MATLAB variables are case sensitive. So capital L is different than lowercase l and such. And also the kilonewtons listed on line 10 is referencing the unit of kilonewtons in the Kornucopia library, where on line 13, that's a variable that got defined by the k-units variables command on line 3. Now what I'm showing is if we were to execute that, in the command window, lowercase l and f would appear just like we had assigned them, 30 inches and 3 kilonewtons. But capital L and F, because we did math, they would be computed, and then Kornucopia returns the results in the unit preference we requested, which would be millimeters and newtons in this case. And lowercase lf and uppercase lf produce the exact same results with the output, again, in the output units of the unit preference. The key point here is that Kornucopia handled all the units issues for you. So just one final point to clarify this issue. So when you type in a k-units variable command, Kornucopia is doing the following. It's going to make variables that are using these names. So it's internally doing this for you. And then it's going to put them in the MATLAB workspace, but it first checks to make sure that this isn't going to overwrite some variables that you already have in the workspace. If it finds any of these variables in the workspace, it'll check to make sure that there are already k-units variable like this kind of thing. And if it is, it's fine. If it's not, it will give you an error saying there's a variable already in the workspace. If you pass this check, then it puts the variable in the workspace. And then when you go do calculations, you're doing math, and so then the result will be whatever your unit preference was when you calculate the result. Now, you need to be a little careful when you do this in certain scenarios. So here I'm defining some kind of weight, and then I'm defining the mass as the weight divided by gravity, and I've used capital M as the variable for mass, which is perfectly fine. If I were to have instead have written an equation like this, where little m is W divided by G, then I would be overriding the variable M that I told to make it to be a meter. And so if I then later want to do a statement like this, that'll be fine because that's a statement, that's an assignment. But if I do any math, the math is going to reference the current value of the variable M, which is no longer a meter as I originally did up here, but because I defined it here in the script, later on I tried to use this, it's referencing this variable, which is now some form of mass, and I will get this kind of thing. So you just have to be a little careful. General guidance would be, if you're doing things like with mass, generally don't use little m, use like capital M. That's just a little thing that sometimes will trip people up. So the point here is Kornucopia still understands the unit M, but the variable M has been changed when you did this. Let's talk just a little bit about the units engine and all its capabilities. So Kornucopia is not just some little lookup table thing. It has a true units engine that's based on something called unit signatures. So there are fundamental primary unit signatures that exist in physics, like time, mass, length, current, and such. There are a few other extra signatures that aren't really fundamental but are useful to track. And Kornucopia's units engine and features manage all that for you, all behind the scenes. So this is much more than just a simple unit conversion table. It actually tracks them. That's why Kornucopia could tell when you had the x squared instead of x cubed in the formulation that there was a units incompatibility error. And it's also why you're allowed to easily use mixed units however you want. Kornucopia will handle all that stuff. Kornucopia even has robust processes to handle issues with temperature, including affine unit conversions, which is the whole issue that occurs with Celsius and Fahrenheit temperatures, as opposed to using Kelvin and Rankine, which are absolute forms of temperature. In the library, there are literally hundreds of predefined units. So units that you're accustomed to, like millimeters and newtons and pounds force and such. And then some more odd ones like Slinch, fortnights, and cotton count. They come from a variety of needs and a variety of industries. You can also easily add your own definitions. So let's say you're doing a lot of work with the speed of light. You can define a unit that c equals this, and then that will be part of the units thing. And you can do Cantor units 35, comma, quote c, and then that would be 35 times the speed of light. Or you can define a mil, which some people in the military use, which is different than the lowercase mil, is a form of an arc angle measurement. It's quite simple for you to control the units within the output via either the unit preference approach, which I've shown, or the dot convert method, which I've also shown. So you can easily define your own units preference or use one of the many predefined ones, which I will highlight in literally just a couple more slides. So if you open up the help system in Kornucopia and you look in the all about units part and then scroll down to the units library and unit preferences, you can look at the detailed definitions of every unit that Kornucopia has predefined. It'll tell you the name of the unit, the formula, in terms of the formula, in terms of a short formulation. It's the same thing. It's just really relative to digits and resolving it from the original statement to some fundamental units usually. A verbal description and what form of unit group does it belong to? Is it an angle, a pressure, a mass, an energy, a force, things like that. Now, one of the things that people will likely be potentially using is the unit of G, which, depending on what you're doing, might be a standard gravity, a standard unit of acceleration for gravity, or maybe it's G for gram. Because that's so ubiquitously used in both camps, in Kornucopia, we've chosen not to include a single unit of G as a known unit. So instead, for grams, we have GM, and kilograms for kilogram mass. And if you're a gram force kind of person, we have GF and GMF. Those both are gram force. And if you're dealing with fabrics, GPD would be a gram force per denier. Or if you're doing ballistics and stuff, you might be interested in a grain for mass. And then if you're dealing with acceleration, capital G would be the standard unit of gravity. Kilo-G with a capital G would be 1,000 units of gravity. And milli-G with a capital G would be 1/1000th unit of gravity. So let's clarify just a little bit more about the units preference. That's an important feature of Kornucopia. And so I want to reiterate, K-units engine can allow you to easily work with mixed units. So you can make a variable A as 5 millimeters times 3 inches. So as long as the variable mm and in was known, Kornucopia would readily do this. Kornucopia would also readily compute with units of newtons per foot squared. Now, when you did this thing, you're doing math as well as here. So the result won't get stored in terms of necessarily millimeters or inches. And in fact, think about this first one here. What should the answer be stored as? Millimeters or inches? Or maybe feet or miles or yards? It's not obvious. So the way that Kornucopia knows what to store this in and represent it back to you is based on your unit preference. So a unit preference is like a unit system, but it's much more flexible. In a unit system, everything is strictly related to each other so that it's all consistent. In a unit preference, you can have inconsistent relationships. So you can have a unit preference that has things like I want length to be in terms of inches, but I want forces to be in terms of newtons. You can do that kind of thing with a unit preference, and Kornucopia will handle that all perfectly fine. So this is just what I just referenced. And then there are many installed Kornucopia unit preferences. Most of those are defined on a consistent set of units, so they look like unit systems, but there are some preferences that are not. Ones that end in _V, which includes voltage for English systems with pounds force and such. And then any of the ones with shock and vibration at the beginning, those are not consistent set of units because gravity will be in terms of G, not in terms of meter per second squared or inches per second squared or things like that. So there are a variety of functions that are used to help you work with unit preference. You can get a list in the software live, as opposed to looking in the help system. I just will show you the help system in a moment. Actually, I'll show you the list live here in a moment. You activate the preference that you want to have active during your calculation. We already used that function. You can ask what is the current active one. In case you've been calculating a while, you open up a couple different scripts and you're not sure what's the current active one, you can inquire, and you can define one. So if you were to type K_units preference list in the command window, you will get this list to echo to the screen. You would then use these names when you're doing things like I want to activate a particular preference, you reference the preference by the name. You can also feed a preference into the conversion method so that you have like some array with a whole bunch of columns of stuff and you say, I want to convert it into a particular preference. You can just issue the convert command and put in as the argument the preference, and then all the data gets converted to that preference. That would be for purposes of displaying things in units that you like to see stuff in. And you can create your own preference. It's quite easy to do that. So if you were doing shock work, for example, this would be a common preference. So what you have in here are some of the fundamental things like millimeters, grams. So this is, length and mass, and a few other fundamental units. We have some stuff related to temperature. And then we have other common combination units like megapascals would be a pressure, right? This would be the inverse of pressure. This would be voltage and ohms for resistance and some other electrical like units. We've got frequency information and things like that. All these units would be in the preference. So you have full control over that. And if you do a calculation that the units do not fit any of these combined things, it will return a unit that's a multiplicative and divisional combination of the fundamental units of the preference, which are always listed at the beginning of the preference. So just a couple of comments. So here I'm making an array of some values. And then I'm saying P is K units. I'm doing an assignment. Take those data and specify these units specifically. So I'm not doing any math, I'm assigning. So when I get the result of that, I get exactly what I assigned, those values and those units. Now, if I go here and I say, I want to reference the column of stress in P, and I want to convert it to KSI and store it back in the column of stress for P, then all of a sudden P becomes like this. And Kornucopia has converted the numbers here to these numbers for the unit of KSI. Now, if I did something incorrect, like I said, I wanted to convert to newtons, Kornucopia would give you error telling you you can't convert this, which is units of stress or pressure, to units of force. So Kornucopia would give you an incompatible units error. You could also do these kind of commands. So here I'm telling it to convert each of the columns for the time, stress, and the vertical length. I'm converting all three columns to hours, gigapascals, and millimeters. Here I'm converting to a unit system. So whatever in the unit system was the unit for time, that's what this column would get converted to. Whatever in this system was the unit for stress or pressure, that's what this column would be converted to, and similar for the length here. If I put nothing in the arguments of the dot convert method, then it will convert it to the default unit preference that is currently active. And if you want to find out what that is, you echo this command and it'll echo it into the command window for you. So that was some fundamental stuff. And now we'll get to a little bit more exciting stuff, which we'll start to read in some data files. So the first flavor of data files we'll read in will be the infamous spreadsheet, and we'll use a MATLAB wizard to import a spreadsheet and then turn it into a K-units data type. And then after that, we will switch to importing, well, not after that, a little bit later, we will demonstrate several Kornucopia functions to read in data from text files, as well as how to read data directly from Abacus ODBs if you're an Abacus user, or Spectral Dynamics data acquisition software files if you're an SD Impacts user. So we'll first start with importing data from a spreadsheet. So in the files you were given, there's a folder called data files. And in there is a spreadsheet, tension test.xlsx. And I've opened up in MS Excel that spreadsheet, and I'm showing you a view of the spreadsheet. This is kind of like a typical spreadsheet that somebody might have. It's not in any specific special format, but it has things that are usually put in spreadsheets. Hopefully there's some information that's like about like where the data came from or whatever. Then there might be, not always, but there might be some section that has some information about some additional dimensions or some other parameters that's common to the data. And then there will be some tabular data. The tabular data will have columns and units. Now, whether or not the units are defined like this nicely with the data, or the units are descriptively written up here somewhere, that will depend on the Wild West. The example I'm demonstrating here is something that is often done, but not always, which is the people will put it in a tabular-like way in the file with column names and units, and then the data itself. So we're going to open up in MATLAB the wizard, and we're going to read that file and import it in. And so I'm going to switch to a little live theater here, and I will do this live in MATLAB, and we'll see kind of what our choices are and what happens when we try to read this in. So I'm going to first clean up the workspace. And we don't need this anymore, so we'll get rid of that. All right, I'm still going to open up the editor so I can type in some commands when I want. All right, so I'm sitting here in this folder that I made a training folder on my computer, and within it I put this Kornucopia ML quick start to put some of the files that like you might on your computer for this class. And in this folder, data files, open that up. There's some files, there's an Abacus ODB, and here is a spreadsheet with this tension test data that I just showed you. We're going to open that up in MATLAB, and we are going to bring it into the wizard. So on the home panel here in MATLAB is the import data wizard. So I'm going to open that up. I'm going to scroll into here, and I'm going to say open up that spreadsheet. And so MATLAB is going to present to me a view of the spreadsheet. And it has a variety of settings up here, which we're going to control. So the first way we're going to read this in is the way most people like to read in data, which is read it in as an array of numbers, a numeric matrix. Now, in this spreadsheet, the top information doesn't have any numbers. It's not numerical. There happens to be one number here, which is kind of a fluke. And the rest of this stuff, there's no data that MATLAB sees as numerical. It only sees an array of numbers down here. So we're going to make a little setting change here, and we're going to tell it to start at row 13. And so now it'll just have an array of data at row 13. If we left it where it was, trying to start way up here, it would have filled where all these sections are. It would have replaced them with a nan, which is not a number. And then you'd have an array with a bunch of nans, which is a little bit of an annoying thing. So we're going to import it like this, and we're going to import our selection to get data, because traditional MATLAB users like to just get data. I could also save this or whatnot. I'm just going to import it. So now the wizard is done. And the variable tension test, which was derived from the file name, is now in my session. Now, normally a MATLAB user would click here to look at the data in the variable editor. If they were to type tension test over here, they'll see that the data just spews across the screen. Not super helpful. If I just do a short portion of that, like I'm doing the first 10, we'll do the first 5 rows and all columns. So this syntax is taking the variable, I'm saying go from row 1 to row 5. That's what this is. And then this means all something. So since it's in the second spot, it's all columns. And it echoes out the data. But you, looking at this, you can't tell me anything about the units, column names, or anything. So having done that, we want to now turn that into a k-units data type. So from our knowledge of what was in the spreadsheet, which we could also right-click on this, and we could say open outside of MATLAB, which means it'll open up in whatever spreadsheet tool you have, which on my computer is Microsoft Excel. So here's our thing. So we really know that we have time, load, and extension in these units. So I'm going to take the data, which we just imported in as numbers, and I'm going to turn that into a k-units entity. So I'm going to be consistent with what I created. We're going to make a variable raw_1. And it's going to be equal to k_units. So I'm going to reference this tension test data. So that's a variable, which is an array of numbers right here. That's our data. Now, what were our 3 units? We had seconds, newtons, and millimeters. Those were the units. And then we had column names. And the column names were time, load, and extension, which was abbreviated as EXT. Oops, missing one extra dot. And then I'm going to make a description. Now before, when I type description, I type the whole word. So here I'm just going to type short, and I'm going to explain why that works in a second. And I'm giving it some description, tension test. Okay. So now when I've done that, if I want to just echo it in the script, I could just type raw_1. I could also type raw_1 over here. But if I do this like this and I just run this, back to the editor, it echoes the data. So if we compare that to this, what we see is we have a much richer description of our variable. It has units. So if we do some calculations, Kornucopia will help us, as we've already demonstrated. If we go plot this, Kornucopia will automatically label the plot with these names and units and stuff. So you'll have a much richer information that you're looking at from a plotting perspective. Now, when we do it to the command window, we only see a part of it. But the intent here is you're seeing the important essence, like some descriptive information at the beginning and an idea of what the data is. If you really want to see all of it, we can use something called the Kornucopia variable viewer. And in fact, we can either put in the variable we want, like this, or we could literally just execute the command without any variable, and it'll pop up a selection of all the variables in the workspace to pick from. If I pick raw 1, it'll produce a nice pop-up that will show me the variable in a scrollable table that I can look at. But it's nice informed information. Now, this is a variable viewer. I cannot edit this, but I can look at it. I can view it. If we compare that to looking at raw attention in the variable editor, it looks like just an array of numbers. And if we look at the Kornucopia data set, it will be presented to you as though it was a structure. So it'll show you different elements in there. And if I click on here, I get the data. If I click on here, I get the units. If I click on here, I get various properties. And if I pick the column names, I'll see the column names. So in general, this is not a very helpful view. And you also should never in Kornucopia go into here, like into the data, and edit the data here. You always do that by commands. If you edit the data or column names here, you can break some of the internal tracking that Kornucopia uses. So in general, with Kornucopia, you would not look at variables in the variable editor that are Kornucopia variables. You'll use the Kornucopia variable viewer, or just easily type over here in the command window and echo them. They won't spew down the screen. They'll just show a small list. And you do have the ability to control this list with this function here, where if you set n to 3 or 4, then it would only show the first 3 or 4 rows of the variable. Now I want to import the variable a different way using MATLAB's variable editor, or not variable, MATLAB's wizard. So we're going to use the same wizard, but this time we'll read it in as a MATLAB table. So we'll just clean up our space a little bit. And we will import with the wizard. Again, we'll point at the same file. But this time we'll import it as a table, which turns out to be the default that MATLAB will try to offer for you. So in the table, you still see there's a whole lot that MATLAB doesn't want to import. For a MATLAB table, the column names of the table are called variable names. And this setting here tells MATLAB what row in the data file to use for deriving these column names. So we wanted the variable names to be from row 11. So if we put 11 in there and hit the tab, then it will make the names for the columns based on what data is in row 11. Now, we still don't want to read in the table and have a bunch of nans. We still want the numbers. So we go down here and we still put this at 13. So it's going to get the data. It's going to give us appropriate column names. And the variable automatically will change since tension test already is there. It's going to say tension test 1. To be consistent with the notes that you have, I'm going to change that variable name to be tension test underscore T representing a table. There's nothing magical about the name. It's just useful. And we're going to import this. A key point that I'm making here is we still don't get all the information imported. So we import that. And now what do we have? We have this variable raw attention T. So if we look at it here, it will show us column names. There's no indication whether units were brought in or not, or any other information. And if we echo it to the command window, we'll have a similar experience as the other thing. It'll just echo the whole thing to the command window. Now, if I want to turn that into a Kornucopia variable, I would simply issue a command like this. I'm going to call this raw number 2. And I'm going to send in the whole table. And what I'm going to do is I'm going to use MATLAB syntax, of curly brace, colon, comma, colon, curly brace. So this syntax in MATLAB for a variable that's of type table, what that tells it is, says, give me all the data, all the rows and all the columns, all the data inside the table, give it to me as data. So give me the guts. So that's going to be just basically an numeric array. And then we're again going to define the units because they were never imported. This time for column names, instead of us manually typing them in, we could leverage the fact that the table has what are called properties, and one of the properties is variable names. That's the cell array of variable names. So I could type in here if I wanted to, tension test underscore t dot properties. I'm hitting tab completion to do this. Not variable names. Oops, variable names. So the variable names, that will give me the cell array of the variable names. And I'll keep the description to be tension test. No reason to change that. So now if I execute that, and now say what's in raw 2, it looks the same as before. And in fact, I can issue a check. So I'll assign a variable check is equal to, MATLAB has a function called is equal, and it tells you if two entities are equal. So is raw 1 equal to raw 2? And when you do is equal, that looks at the whole variable as a whole and gives you a single logical answer. If I did the double equals approach, that would look at every element within each variable. So this is just looking at the whole, at each variable as a whole. And it comes back with a logical 1, which means true, which means I came to the same result. One case was dealing with a table. One case was just dealing with an array. So the point being, if you have some data in Excel, you could copy the data from Excel. Literally, let me just open that up in Excel and do it that way really quick. So I'm going to open this file up in Excel. I could literally have just grabbed this data. I'll just grab a small portion of it for the demonstration, grab that data in here, and then I would have had to have pre-made some variable. So let me just pre-make a variable to paste this in. So I'll make a variable Bob equals 1. So now I have a variable that's a double, so I can go in the editor if I really wanted to do this. And I can say paste, and I've pasted the data from Excel in there. If you want to do that kind of thing, that's fine. And so now Bob has that data. And once Bob is now an array of data, I could do the same kind of thing like I'm doing here with an array of data. So those are 3 ways to get stuff in using normal MATLAB flows, get it into an array, and then put it into a K-units data type. That concludes part 2 of our Kornucopia ML Quick Start training. Please continue with our next video, part 3, via the link provided on our website.